Hello, everybody, and welcome to another video on machine learning in biotechnology. My name is Ian Hoffecker, and this session is going to be about deep neural networks. So the topics I want to cover are first a review of the supervised machine learning pipeline that we've been through now with linear regression and then logistic regression. And we're going to kind of build off of these ideas for neural networks. And so on the topic of neural networks, we're going to talk about what makes them different, their capacity to handle non-linearity in parameters, and we'll talk about a simple type of deep neural network, the multi-layer perceptron, and how this can be used to approximate nonlinear functions and also Boolean logic gates. And then we have an exercise for you based on that. And then we will keep talking about neural networks, and we'll focus on some of the training and troubleshooting practicalities, the things that you are likely to encounter in practice when dealing with neural networks. But today is going to be all about the intuition and the basic understanding of what is going on in these things and how to build them and how they work fundamentally. So first, let's review the kind of general pipeline which we're going to be building off of. So in linear regression and logistic regression, we had kind of the same thing going on where we have some kind of model. So that's going to be a variable that we want to predict, typically call this y. And in logistic regression, this was a class label like 0 or 1. In linear regression, this was some kind of continuous variable. It could have a number. It would be a number, could be anywhere from -infinity to infinity. And we have some kind of mathematical formula that is going to relate our input data x to this predicted variable y. And it's going to be modified by other numbers, parameters, and we're typically calling these weights and biases in this field. And the idea is that this transformation of the input with these parameters is going to end up accurately predicting our modeled variable y if we somehow choose the right values for these parameters. And so the framework that we've been following is the one based on probability theory. So there's other ways to kind of think of machine learning, but this one is a nice one grounded in statistics and probability. And the idea is that we formulate our model first as a likelihood expression. In other words, we're interested in optimizing the probability of observing our training data given a set of parameters. And by tweaking those parameters, we can increase this likelihood or increase this probability. And those parameters that we're tweaking, again, are these weights and biases. And we have a training loop that's going to happen many times iteratively. And these iterations we're calling an epoch. And the idea is that in the first phase of the epoch, we're assessing our model. So we're going forward through the model. So we have an equation. It takes an input x. We have a set of parameters. Maybe they're just initial parameters, initial guesses. They might be really bad to start with. But anyway, we're going to feed everything through the model and produce a prediction for our y modeled variable. And then we're going to use some kind of loss function, right? Or a cost or score function. And the idea is to compare the predicted with our training output data, which is sort of the answer key. And the more different they are, the worse our loss function is, or the higher the loss is. And the goal is going to be to minimize this systematically. And the way we're going to do that is by taking progressively steps towards lower and lower values of the loss function. And the way we do this is by computing a gradient. So gradient is a type of derivative. So it's a measure of the slope or the rate of change of the loss function with respect to the parameters. So you might have many parameters. So basically, this is going to be a big list of all of the ratios of how much the loss function will change with respect to these individual parameters, or how important each of these parameters are in affecting the value of the loss function given their current value. And so then when we have these gradients, these rates of change, we're able to take a step in parameter space, or in other words, make small adjustments to each of our parameters that will move the loss function towards the minimum, hopefully a global minimum. And we do this by multiplying a step size or a learning rate to the gradients that we've calculated in the previous step. And so now we have an updated set of parameters, and the idea is we go back to step one and we repeat the whole thing over and over again. We would keep doing this until either our loss function stops changing or we reach some satisfactory value. And then this would ideally, hopefully, represent a state of the model that is performing well or predicting our modeled variable y with some high degree of accuracy. So if we kind of go back and just review how this looked in linear regression, right? So we had this initial model. So we had this predicted variable y, and the computation here was on this set of weights and a single bias term and their multiplication, element-wise multiplication with your input variables, which there could be any number of them. And the idea here is this is a linear combination. So we're summing these terms together, summing these features together. And what we can do is then formulate this as a likelihood expression. So we said that actually this is akin to a Gaussian distribution with a moving mean parameter. So instead of a fixed mu here, as you might have for a single Gaussian distribution, we have this linear combination of terms here, or the equation for a line basically dictating the position of this mean. And in our likelihood expression, we're representing the probability of observing y given some set of parameters and an input x or a set of x. It's a multivariable case. And once you have this likelihood expression, we can then transform this into a loss function. So we're interested in maximizing this probability, which is the same as minimizing the negative log that probability. So this we call the NLL, or the negative log likelihood. And the idea here is that it's log, so that we're allowed to use summations here. And it's a negative number, meaning that we're searching for the minimum. And in the case of linear regression with a symmetric Gaussian distributed variable that's distributed symmetrically over this line here or over this mean, then you could use, in that particular case, you could use a simpler loss function here, which was this residual sum of squares. But the more general case, if you have, say, a non-Gaussian distributed variable, you could use the negative log likelihood. This could apply more generally to something like, say, a Poisson distributed variable, not just a Gaussian. So that was linear regression. And then we then moved on to logistic regression. And the idea here was that we're no longer interested in modeling a continuous variable function, predicting some kind of function. What we want is a class label instead of this continuous function. And it's going to start out very similarly. So we have this linear combination of terms, just like with linear regression. But instead of this being the goal is to take this one step further and map this onto a scale from 0 to 1. And we would do this using this sigmoid function, which takes whatever value we have here, this A pre-activation value, and squash it into a range from 0 to 1, or this S-shaped curve. So we map A onto this S-shaped curve. That gives us a probability. And then our loss function becomes a matter of maximizing the likelihood of observing the class label 1 given X and our weights. And for this particular case, for the sigmoid function here, we had a solution to the gradient, the negative log likelihood, which we could then use to quickly compute the steps that we should take towards the minimum in order to maximize the likelihood. So that's kind of the algebraic perspective, the way to view these models in terms of equations. But we can also use this graphical method here. So linear regression can be represented as a graph or a network here, where we have any number of input variables, x0, x1, x2, that are being summed. So we have a summation here, and this is the output. But in order to get to the output, these inputs are weighted. So we're applying weights as well as a starting value of the y output here, or otherwise known as the bias. So we add the bias and we add the terms, each weighted by their weights, and that's going to give us our output here. And the logistic regression is going to look very similar. So architecturally, it's the same structure here, except that we have one additional step. So after this summation, we're going to feed that pre-activation into an activation function, or sigmoid here. And so the output of the logistic regression is going to be this probability now instead of just the summation. And you can take this further and convert this probability prediction into a classification by making some sort of call, picking a threshold, say 0.5. Anything above 0.5 is a 1, anything below is a 0. And then we can use this to make decisions. So linear versus nonlinear. So earlier we talked about what makes something linear or nonlinear. And we said that actually you could use linear regression to do, say, polynomial fitting, where you have a function like x squared, x square root of x. And the way you can get away with this is because you're still linear in the terms. So we're still performing a summation or a linear combination of these terms, where all of the parameters we're interested in are outside of these nonlinear functions. And as long as this was the case, then you could still perform this linear regression, and this could be a way to model nonlinear functions. But at some point, you're a bit restricted here. So this would mean that you would have to pre-decide the functions here. So if we said it's x squared, then we would not be allowed to change the value of that function. And one could imagine a more adaptive situation where, in addition to training or manipulating the parameters outside of these functions, we might have a set of internal parameters where we could modulate those as well. So imagine if instead of x squared, we have x, and then it's some variable parameter that we're allowed to change. So this is not exactly what is happening with neural network, but this is very similar. So the basic idea behind deep neural networks is that we have nested parameters, nested functions. So the function that we're interested in is going to be determined by a function of a function of a function, and each of those functions correspond to layers in the neural network. So this is going to allow us to more finely divide our space, or divide our space with more freedom. And there's all sorts of functions out there that cannot really be captured by linear regression or logistic regression. So these include all sorts of surfaces and shapes and manifolds, clusters of data that are very typical to observe in biology. And so this is the whole idea behind deep learning, that we have these hidden layers. We have this structure here. We again have the inputs and output similar to what we saw with linear regression and logistic regression, but now we've simply added more to this. So we have hidden layers, and one can think of these as intermediate parameters for deciding on the output. And we're able to capture much more variability in the data this way. Okay, but so let's get more concrete here. So the hope here is to get some better intuition for what's actually happening. So let's take a specific example. So here we're sticking to, as closely as possible, something that we're familiar with. So the logistic regression, except now in this case, we have a single input x here. And now we've created a hidden layer. So we have two nodes here, H1, H2, before getting to the output layer, as opposed to, say, a univariate logistic regression where it would be X going straight into Y here. And so each of these H1, H2 are going to have their own logistic regression sigmoid function on them. And the Y output here, we're not going to feed this one through an activation function or anything. We're just interested in directly computing the output value here. So doing a kind of continuous function approximation here. And so the test data that we've fed in here, the training data here, is this parabolic function here. So the goal is to approximate this, which cannot be done with typical linear regression, although I would say that you can do this with the polynomial regression using linear combination of terms still. But the idea here is we're going to do this with a neural network this time, and we're going to pick apart everything and look at exactly what's happening. So if we write out the equation here, once again, we can see that it's a linear combination of terms if we just look at this outer portion here, right? So we have this weight times some input plus another weight times some input plus some bias. And then if we open up what's going on inside these portions here, we see that there's an activation function, a sigmoid over here, and inside that, another one of these logit pre-activation linear combinations of terms. So we have another weight times x plus a bias, a weight times x, be a plus sign there, plus a bias here. And so these are actually the values that are getting computed by H1 and H2. So we can see that weight 1, x is going to H1 via weight 1, 1 here. And we have a bias, that's the starting value of H1 here. And we have a similar thing going on H2 here. So x1 is going to H2 via weight 1, 2. And we have a bias weight B2 here. And so those individually could be thought of as a small logistic regression. But now those two are being used as the inputs now to Y, our output here. And if we look at what's happened, so after the training, so we're kind of skipping that for now, but training has happened and the weights have been optimized. And what does it actually look like? What's happening? So you can see there are two sigmoidal curves here that have kind of lined up next to the curve here. And there are two of them because we have H1 and H2. So there are two sigmoids involved in this network. And they've been placed in such a way that they would reduce the loss function as much as they can. And this is sort of the limit of what you can do with these two nodes, these two activation functions. But you can see that at least in this range here, we are able to kind of approximate or predict the value of y here for a given value of x. And then the model breaks down in other places. But this is the basic idea. And if we want to get a better approximation, we can see here that we can do that by adding more sigmoids. And we do this by adding more nodes in the hidden layer here. So each one of these corresponds to another sigmoid. The weights and biases on each of these nodes here corresponds to the slope inflection point and shift or translated position of each of these sigmoids. So you can imagine the knobs that you're tuning here are basically the angle and position of each of these sigmoids that are getting added on top of each other. And so that's one type of activation function that I use because we've been through it before, the sigmoid, but turns out there are many activation functions, and all of these are chosen for their ability to create nonlinearity, or the ability for you to place them in space and have them not affect all of that space. So one commonly used activation function is ReLU function here, and the idea is that it's simply just whatever the input is, unless it's below 0. So if it's below 0, if your input is below 0, then you just set it to 0. If it's above 0, then the output of a ReLU activation function is simply the value of the input. Or another way you can write it is it's the maximum of the tuple A and 0, where A is your input. So if A is negative, then it's 0. If A is positive, then it's A. And this basically allows you to place lines anywhere in space, little line segments. And this can then be used to get a nice approximation of, for example, this parabolic function that might be less awkward, say, than these sigmoids, which are not really perhaps ideal for this. Okay, and so this is continuous variables. So in the output in y, in that case, we said we're not feeding it through any kind of activation function. We're just looking at its value. And so we're interested in that continuous variable. But we can also create a classifier similar to the logistic regression. And the idea here is that we're going to do everything basically the same, But in the last output value, we're going to use, again, this sigmoid function to create a binary result out of whatever final pre-activation is fed in there. And so why might we want a neural network instead of, say, logistic regression to achieve this? And the answer is that we can achieve much greater complexity of logical relationships in our inputs. And I think sort of the most interesting way to think about this, in my opinion, is to think of it as a form of computation. So one thing that neural networks are capable of is replicating Boolean logic. So Boolean logic, like these gates here, are sort of the atomic elements of computation. So basic circuits, integrated circuits, modern computers, they're all based on this foundation of logic. So relationships, for example, like the NOT gate. So you have an input. If it's 0, then your output is the opposite of that, or 1. If your input is 1, it's 0. You have things like the AND gate over here, which has 2 inputs, A and B. And if both of them are 1 or both of them are 0, then, or excuse me, yeah, if both of them are 1, then the output is 1. And then if either of them are 0, both of them are 0, then the output is 0. So we can use these truth tables here to model exactly what's going through each of these gates. So here's the XNOR gate, which has this particular truth table here. And the interesting thing about Boolean logic is a few of these gates, so like AND, OR, and NOT, are sufficient for universal computation. So if you have a few of these gates, then you can assemble larger constructs like adders and multipliers. The square root function in an old school hand calculator, for example, has some circuitry in it that is performing a bunch of binary logical operations that ultimately lead to computing the square root. And all of computation is built on this foundation. And while logistic regression can represent lots of fairly complex relationships, for example, you can have many variables, and many of them have small, weak contributions to predicting an output label, a class label. But one thing they cannot do, and this has been mathematically proven, is a logistic regression cannot represent the XOR logic gate. So this is one of the fundamental logic gates. So it's this one here. It has these inputs, 2 inputs, and a single output, right? And if the inputs are different, then the output is true, or 1. If the inputs are the same, 0, 0, or 1, 1, then the output is 0 or false. If we train a neural network that has at least one hidden layer with a couple nodes here, it is possible to model and correctly compute the output that you want from an XOR operation. And so the neural network would look like this. So we can show it here, and these weights have already been solved. So these are the actual weights that you would need to perform XOR using this small neural network here. So we have 2 inputs, x1 and x2, or A and B up here. And we have h1 and, sorry, this should be h2. And each of those have a starting bias. So the starting bias on h1 here is minus 1.5, minus 0.5 on h2 here. And then those outputs are activated with a sigmoid function, and then those sigmoid activation levels are then fed as inputs to a final output, which also has a starting bias, minus 0.5, and a sigmoidal activation function connected to it as well, which is going to decide if it's a 1 or a 0 with some probability. You'd see that each of these lines are also connecting these different nodes with some weight. So it's +1 here for these inputs, -1 here for the h1 to output. And if we want to test this system out, all we have to do is feed in some numbers for x1 and x2 and calculate everything. So we can do this by hand, actually, and it helps to kind of break things into parts. So we first compute h1 here. And so that's going to be the starting bias minus 1.5, and then we go through each of the inputs. So there's x1 is an input here and x2 is an input here. If we look at the three arrows, so there's going to be three terms that we're adding together. And so x1 is weighted by 1. So if we use this truth table, let's test the value 1 and 0. So x1 is 1, x2 is 0. And if we've done everything correctly, if this is truly an XOR operation, then we should get 1 for the output. And if we feed these things in, we get for H1 a value of minus 0.5 here. And we do the same thing for H2. So we sum these three terms, and we get a value of 0.5. And if we feed these through to a sigmoidal activation function, then we now have the inputs needed to compute the summation for the output. And so that's going to be calculated by its bias, minus 0.5, plus these two sigmoidal results, each weighted by their connecting weights here. And if we do that, we get this value of 0.436. And if we look at this, so we have 1, 1, 0, 0 for our truth table. We have 0.436, 0.436, 0.424, 0.424. So if we were to set our threshold between 0.42 and 0.43, then we would be able to correctly classify these inputs as either 1 or 0 according to the XOR logic that we're aiming for. And you can see that we can do this actually just in a spreadsheet. There we go. So here we're testing out different values of the truth table. If x1 is 0 and x2 is 1, then we get 0.43, like I said. If both of them are 0, both of them are 1, we get 0.42. And we can also test out non-binary inputs as well. So what if x1 is 0.97 and x2 is 0.04, so rather close to 1 and 0, but not exactly. And here we get, again, a fairly high value relative to these lower values down here. So this works, which is very interesting. And the fact that this works is just kind of scratching the surface. So neural networks can basically represent all kinds of logic, and we can build on the complexity, and this complexity can also be present in the data. And presumably the idea is that if we can train our networks effectively, then we're able to discover the logic that is present in our data. Okay, but so that was kind of running this pre-trained network, and we can see that it's capable of these interesting things, representing nonlinear functions and complex computational logic. But now it's time to talk about the training aspect of this neural network. So we have more or less similar a process as linear regression and logistic regression. So we want to make a prediction, evaluate the quality of that prediction, and determine a gradient, which is going to tell us the direction in which we need to go to minimize this loss function. And so the tricky part, I guess, here is this gradient computation step. And so this is so we're going to use something called back propagation. And the idea here is that we're going to start with a forward pass. So this is just like linear regression. We feed the input X into our network. We apply all these weights and biases to perform the computation like we did just now for this XOR example, and then we get some output Y. We compute a loss, so now we have this predicted value, and we have set aside some training data, some labels that tell us how well this prediction scores. So this could be, for example, the negative log likelihood. And then we're going to perform a backward pass. And the idea is that we're going to start from the output layer and move our way back through the network and compute the gradient of the loss function with respect to the weights. And so I'll get into this in a second, but the key here, the key concept here is this idea from calculus called the chain rule, which is basically going to allow us to compute the gradient for weights by nesting values of the weights and nodes that we need to connect the weight we're interested in to our output function and therefore also our loss function. But we'll talk about this more in a sec. And then just as with linear logistic regression, we're going to perform an update. We'll take a step. We have some learning rate or step size, and we're going to multiply this with the gradient and then subtract that step from whatever our current value of the weight is for each of the weights and bias. And then we're going to repeat this several times. So what's our loss function in this case? So it's going to be the same routine that we've been doing. So if we're working with a sigmoidal activation function, we can use this negative log likelihood and this solution to the negative log likelihood for a sigmoidal function, which is sometimes called the binary cross entropy. So this is a common loss function for classification problems. And in addition to logistic regression, we can use it for neural networks that have a sigmoidal output. And so if we apply this to a particular case here, so we have this example, say, of a network with one input, one hidden layer with two nodes and one output, and we can then write out a likelihood expression here. So we're interested in the final output, a sigmoidal activation value for an input, and then that input then is going to have these nested quantities here, one for H1 and one for H2, and then a bias applied here. And we can transform this probabilistic model, this likelihood expression, then into a negative log likelihood. So I showed you kind of the general case up here, but for illustration purposes, let's show what this would look like for our particular neural network here, the H1, H2 example. So we would have to open everything out, apply the architecture here to our particular case here. So we have this general expression for the negative log likelihood for sigmoidal function. And instead of y here, we're going to substitute that with the sigmoidal activation of the inputs to y, which is going to give us y. So here it's got all the weights with H1 and H2 here. And then H1 and H2 themselves have their own inputs. So instead of H1 and H2, we could substitute in things in terms of x. So instead of H1, it would be the sigmoid activation of weight 1-1 x plus bias 1 here. And so if we perform all these substitutions, kind of moving back through the network, we get this very long expression here that is only in terms of x and all the weights and biases. So that's our loss function, right? So we want to minimize this just like we would for linear regression or logistic regression. And in our forward pass, we would go through and compute all these quantities. So we can compute H1, compute H2. From H1 and H2, we can compute the prediction for y here, and then we can know how well we're doing, basically what value are we currently at in the loss function. And we would use this expression, this long expression that I just showed. But then to perform the next step, so we want to move towards a lower value of the loss function. And to do that, we want to compute the gradient. And so the gradient, we'll review a bit of calculus here. So the gradient is very related to the derivative. So if we remember back to calculus, the derivative is this rate of change, a slope here of our, in this case, our loss function with respect to some parameter or some weight here. And we want to know for a tiny change in the weight, what is the corresponding change we would see in the loss function. And so the gradient is a kind of multi-dimensional generalization of this concept here. So if we have two parameters instead of just one here, then we're thinking more in terms of three-dimensional move. So we're moving in some direction in the weight 1 direction and some direction in the weight 2 direction. And how much more we're moving in weight 1 and how much more we're moving in weight 2 kind of determines which way in this high dimensional space we're headed. So it's this, looks like this, it's just this list of derivatives of the loss function with respect to each input here. And this should be not x1, this should be weight 1, weight 2, weight n here. And so for the back propagation algorithm that we're going to use for these neural networks, a key concept that we're going to utilize is something called the chain rule. And this basically says that we can compute any derivative here. So for example, the rate of change of the loss function with respect to a weight that we're interested in, we can compute this through as the product of intermediate derivatives here. So dy, this should be NLL. So dNLL du times du dw here. And the way you think of this is these intermediates kind of cancel out, being on top and bottom of these fractions here. And you can chain several of these together. So here, A's cancel, the B's cancel, the C's cancel, and we're left with dNLL dw here. And so even if we have a hard time directly knowing this value here, dNLL dw, if we have a way to know these intermediates, then we can compute dNLL dw. And so that's the big idea here, that we're interested in this. This is the gradient for, this is the derivative for a particular weight. And we're going to want to know this value for all of our weights in our network. But to compute them, we need to get there through intermediate computations. And that's where this chain rule is going to help us. And so the back propagation step here, the word propagation comes from this act of starting from the output value. So we have, we're able to predict, we're able to compute dNLL dy predicted output here. So this is just going to be our derivative of the loss function with respect to the predicted y here. So we have an expression and we can take the derivative and solve for this. And we have all these values available, right? We have the training data and we can compute y predicted because we have, you know, all our parameters have some value. So we can go through and compute this value. So this thing is known, check. And then we can also know these intermediate derivatives as well. So we want to know, say, the change in predicted y with respect to h1. And so we have an expression for y predicted here that's in terms of h1 and h2 here. And we can solve for the derivative, compute the derivative of this, and get an answer here in terms of h1. And we can do this again, move back further and do this now for h1. We have an expression for h1 in terms of its inputs, x, and its weights and bias. And we can compute a derivative there as well. And that way we can get these intermediate values. And then so through the chain rule, the y predicteds cancel, the h1s cancel, and we're left with this value here, dNLL over dw11. And so that's how you would determine the gradient for this particular weight here. And you can use the same process for any of the other weights or biases in the network. So that's what back propagation is going to do. It's going to start first with the output layer, compute all of the derivatives for weights going in, then move back a layer, compute all the weights for h1 and h2 here, again applying these chain rules. And then once you have all of these gradients, we'll do the same thing that we did for logistic regression and compute a step. So we have some learning rate alpha here, and we multiply that with the gradient. So the gradient, again, this big list of derivatives, and then that's going to give us a step size for each of our parameters. So our big list of parameters, we're going to tweak parameter, weight 2-1 by 0.5, weight 2-2 by minus 0.6, and so on. And that's going to give us now the new set of parameters, and we go back to step 1 and repeat. And so we mentioned before that you can sometimes change the step size, and this can be good for training. And so one thing that we're going to use today is something called adaptive moment estimation, or ADAM. And we're not going to think about this too much, but this is a widely used learning rate adjuster that will help us to train our networks faster and more efficiently using less computational resources. And we also mentioned these different activation functions. So one of these is the ReLU function, right? So this is going to have a max of 0 or the pre-activation. So it's going to be equal to the pre-activation above 0 or equal to 0 below 0. And that's the idea behind the ReLU function. And it has also a very simple derivative. So when it's below 0, the derivative is 0. It's not rate of change is not changing. And then it's a fixed rate of change of 1 for anything above 0. And so if you wanted to do this same process here for something with a ReLU function, then you would need to use this derivative instead of the sigmoid derivative. So that's kind of sort of the bottom-up perspective. And then the exercise here that we're going to try is to replicate this XOR logic in the context of a kind of artificial genetics problem. So let's imagine that we have two genes, gene 1 and gene 2, and there's a particular phenotype that we're interested in. And this is class 0 or class 1. And we were to do logistic regression here, we would be interested in correlations, right? So is class 1 associated with a high or low gene 1 expression or a high or low gene 2 expression? And what we're seeing here with this checkerboard pattern is that there's an interaction between the genes. So it's not enough just to know gene 1 expression. That is alone is not going to tell you if you're class 0 or class 1. You need to know if your gene 1 expression is low and your gene 2 expression is high, in which case you'll be class 1, or is your gene 1 expression low and your gene 2 expression also low, in which case you'd be class 0, or vice versa, you flip them. If gene 1 is high and gene 2 is low, then you're back to class 1. So this is actually the XOR logic gate represented kind of graphically here. So we're interested not in high or low, but relatively speaking, are the expression levels different between these two genes? And then that's going to determine class 0 or class 1. And logistic regression cannot represent this because it's only looking for correlations. Is it high or low with respect to gene 1? Is it high or low with respect to gene 2? Never going to be able to detect this type of interaction. So the hope here is that we can use our multi-layered perceptron or deep neural network with a hidden layer to discover this structure in the data. And so the exercise is set up like this. It's going to give you this data from GitHub. It's already set up to split it into training and test subsets. And just for comparison, it will perform a logistic regression that we're going to use to see how well our neural network has performed. And then your task will be to build the neural network using the Keras library. And then at the end, it's going to generate an ROC curve, test the model with the test data from the split. And since it's a binary classifier, the ROC curve is going to tell us how well this predictive capability is based on the area under the curve of this ROC. If it's close to 0.5, then it's not doing well. If it's close to 1, then it's performing well. And so here's just kind of a primer in how we can set up models using the Keras library. So here in Python and here in R. And the way you do this is you create a model object here. So we're going to use this one, sequential. And we build our layers here. So this first step here is adding a 2-node hidden layer to the network. We've specified an input dimension here. So it's understood that there are 12 inputs. And we specify the number of nodes. And we also specify the activation functions here. So we could use ReLU that we mentioned, or we could use a sigmoid. And then an important point here is we want the output to be a 1-node output with a sigmoid function, since we want to use a binary classification here. And then we need to compile the model. So this is done for computational efficiency reasons. And the things we need to specify here is the loss function. So we want to use this one, the binary cross entropy, since we have a sigmoidal activation at the end. So we're trying to evaluate binary classification performance. And then I mentioned we can use this adaptive learning rate, and we can turn this switch on by feeding in this argument here, optimizer Adam, for adaptive moment estimation. And then it's going to train the model with our training data. We'll specify a certain number of iterations or epochs, and then we'll make a prediction. In R, it's going to look very similar. So we create a model object, sequential again. We will use this pipe operator here. So we feed the output of this line as the input to the next line to build the model. So each of these lines here corresponds to an input layer, hidden layer with a certain number of nodes, a certain activation function, ReLU or sigmoid. And then again, we're going to compile the model specifying our learning rate adjustment here and our loss function, binary cross entropy. And then we'll train the model again. So this is how the exercise looks. So everything is kind of blank here, except for the training step here at the end. So then it's up to you to follow these steps and build a model, choose the number of nodes, choose the number of layers, and try to get this thing to work. So that is it for today. And yeah, so to kind of go through things, we have this pipeline, and it's very similar for linear regression, logistic regression, and neural networks, where we have a model, we want to compute the gradient, and we're going to take steps to minimize our loss function. And we have these non-linearities that linear models are not good at predicting, such as XOR logic. And we went over training, computing the gradient using backpropagation and the chain rule. And next time we'll talk more about some of the practical stuff dealing with data and optimizing and troubleshooting some of the trickier parts with neural networks. So that's it, and see you next time.